Antimatter is often treated as a fantasy concept, something belonging to science fiction stories, glowing engines, and futuristic weapons, but in reality it is one of the most rigorously predicted and experimentally confirmed ideas in all of modern physics. Long before antimatter was ever observed in a laboratory, it existed quietly inside equations, hidden in the mathematical structure of nature itself. This is what makes its story so powerful. Antimatter was not imagined to make science more exciting. It was discovered because the universe, when described honestly through mathematics, demanded its existence. At the beginning of the 20th century, physics was undergoing a revolution. Classical ideas about matter, motion, and energy were no longer sufficient to explain what scientists were observing. Einstein's theory of relativity had already reshaped our understanding of space and time, showing that energy and mass were deeply connected. At the same time, quantum mechanics was emerging, revealing that particles did not behave like solid objects, but more like probabilities, waves, and mathematical patterns. It was in this intellectual storm that the foundations of antimatter were laid. When physicists began combining quantum mechanics with special relativity, they faced a serious challenge. Equations that worked perfectly well at low speeds began to fail when particles approached the speed of light. One of the most important breakthroughs came from Paul Dirac, who attempted to write an equation that could describe electrons while fully respecting Einstein's relativistic principles. Dirac's equation was elegant and powerful, but it carried a shocking surprise. Alongside the expected solutions representing electrons with positive energy, the equation also produced solutions with negative energy. At first glance, negative energy made no sense. If electrons could fall into these lower energy states, they should release infinite energy and collapse the universe instantly. This was clearly not happening, so many physicists suspected the equation was flawed or incomplete. But Dirac trusted the mathematics. Instead of forcing the equation to fit existing intuition, he allowed intuition to be challenged. He proposed that these negative energy states were not empty but filled, forming what became known as the Dirac sea. A missing electron in this sea would behave like a particle with positive charge. This was the theoretical birth of antimatter. What makes this moment extraordinary is that antimatter was not discovered by looking through a microscope or telescope. It was discovered by listening carefully to mathematics. The equations did not offer antimatter as a possibility. They demanded it as a necessity. This marked a turning point in science, showing that reality could be stranger than imagination, and that mathematics could reveal truths about the universe long before experiments caught up. The real test of any scientific prediction is experimental confirmation. In 1932, Carl Anderson detected a particle in cosmic rays that behaved exactly like an electron but carried a positive charge. This particle, the positron, was the first confirmed antiparticle. Its discovery instantly transformed antimatter from a theoretical curiosity into an undeniable physical reality. What had once seemed like an abstract mathematical artifact was now leaving tracks in photographic plates. This moment shattered the idea that antimatter was speculative or fictional. From that point onward, antimatter became a measurable, testable part of physics. Scientists began discovering antiparticles for nearly every known particle. Protons have antiprotons, neutrons have antineutrons, and even more exotic particles follow the same pattern. Each discovery reinforced the same message. Antimatter is built into the structure of nature itself. Richard Feynman entered this story not as the discoverer of antimatter, but as the physicist who made its meaning clearer and more profound. While Dirac had introduced antimatter as a solution to a problem, Feynman revealed its deeper implications. He showed that antimatter was not just a mirror of matter, but a clue about how time, causality, and interaction truly work at the quantum level. One of Feynman's most mind-expanding insights was the idea that antiparticles could be interpreted as particles moving backward in time. This was not meant as science fiction, but as a valid mathematical interpretation of how particles behave in quantum equations. When calculations were performed, treating antimatter this way made the math simpler, cleaner, and more intuitive. The equations did not change their predictions, but their meaning became richer. This interpretation did not imply that we would see particles literally traveling into the past in everyday life. Instead, it revealed that the laws of physics do not strictly distinguish between forward and backward time at the most fundamental level. Antimatter exposed a hidden symmetry in nature, suggesting that time itself might be more flexible in equations than in human experience. This idea alone forced physicists to rethink what they believed about reality. Feynman's work also demonstrated that antimatter was essential to understanding how particles interact through forces like electromagnetism. His development of quantum electrodynamics showed that interactions between charged particles could be described as exchanges involving virtual particles and antiparticles. These processes, though invisible, could be calculated with astonishing precision. The results matched experiments to an accuracy unmatched in any other field of science. This precision is one of the strongest arguments against the idea that antimatter is speculative. The predictions involving antimatter are so accurate that they have been verified to many decimal places. When theory and experiment agree this closely, it is a sign that the underlying concepts are not approximate guesses, but deep truths about the universe. Beyond the laboratory, antimatter plays a role in some of the most fundamental questions in cosmology. According to modern theories, the Big Bang should have produced equal amounts of matter and antimatter. If that were true, the two should have annihilated each other completely, leaving behind a universe filled only with radiation. Yet here we are, living in a universe dominated by matter. The fact that anything exists at all suggests that something tipped the balance in favor of matter. This mystery, known as the matter-antimatter asymmetry, is one of the greatest unsolved problems in physics. Antimatter, far from being a fictional idea, sits at the heart of this cosmic puzzle. Understanding why matter one requires understanding antimatter in exquisite detail. Every experiment that studies antimatter is also an experiment about why stars, planets, and life exist. Antimatter also proves its reality through practical applications. In medical imaging, positron emission tomography relies on antimatter to detect diseases inside the human body. Positrons emitted from radioactive tracers annihilate with electrons, producing gamma rays that doctors can measure to create detailed images of organs and tissues. This is not speculative technology, it is everyday medicine, saving lives across the world. Particle accelerators routinely create antimatter in controlled environments. Antiprotons are produced, trapped, and studied with extreme precision. Their properties match those of protons almost perfectly, except for charge. This symmetry confirms the predictions of fundamental physics again and again. Antimatter behaves exactly as the equations say it should. The popular image of antimatter as dangerous or explosive is rooted in misunderstanding. While matter-antimatter annihilation releases immense energy, antimatter itself is not inherently unstable or violent. It only reacts dramatically when it encounters matter. In isolation, antimatter is just as calm and orderly as ordinary matter. This fact further strips antimatter of its fictional aura and places it firmly in the realm of normal, if exotic, physics. What makes antimatter so unsettling is not its danger but its implications. It tells us that nature is symmetrical in ways that challenge human intuition. It tells us that equations can reveal entities we never imagined. It tells us that reality is not built solely from what we can see, but from what must exist for the universe to be mathematically consistent. The story of antimatter is therefore a lesson in humility. Humans did not invent antimatter to solve a practical problem or entertain an idea. Antimatter forced itself into our understanding because the universe demanded it. When physicists tried to describe reality honestly, without cutting corners, antimatter appeared as an unavoidable consequence. This is why antimatter is not science fiction. Science fiction begins with imagination and asks whether reality could support it. Antimatter began with reality and forced imagination to catch up. Its existence reminds us that the universe is deeper, stranger, and more precise than human intuition alone could ever predict. In this sense, antimatter represents the triumph of scientific thinking. It shows that by trusting evidence, mathematics, and logic, even when they lead to uncomfortable conclusions, we can uncover truths that reshape our understanding of existence. Antimatter stands as proof that the universe is not obligated to conform to common sense, only to its own internal consistency. As experiments continue and theories evolve, antimatter remains a central character in the story of physics. It is a reminder that the most revolutionary discoveries are often not found by looking harder at the world we know, but by questioning the assumptions we take for granted. Antimatter emerged when physicists dared to believe that equations could reveal reality, even when that reality seemed impossible. And perhaps that is the most brain-breaking truth of all. Antimatter was not discovered because humans were clever enough to imagine it, but because the universe itself insisted on being understood as it truly is. Antimatter becomes truly unsettling when we realize that it is not a violation of nature's rules, but a perfect reflection of them. One of Richard Feynman's most powerful contributions was clarifying that antimatter obeys exactly the same physical laws as ordinary matter, with only certain fundamental properties reversed. This idea sounds simple on the surface, yet its implications reach deep into the foundations of reality and quietly dismantle many assumptions about how the universe should behave. At first, it seems natural to imagine antimatter as something exotic or unstable, as if it belongs to a different universe with different rules. But Feynman showed that this intuition is misleading. Antimatter is not governed by new physics. It is governed by the same physics, written with remarkable symmetry. An antielectron, or positron, has the same mass as an electron, responds to forces in the same way, and behaves identically in motion. The only difference is the sign of its electric charge. Where an electron carries a negative charge, a positron carries a positive one. This reversal alone changes everything, yet leaves the underlying laws untouched. This symmetry is not accidental. It emerges naturally from the equations that describe the universe at its most fundamental level. When physicists write down the mathematical laws governing particles, those laws remain valid if certain quantities are flipped. Charge can reverse, spatial directions can mirror, and time itself can run backward, yet the equations still hold. This deep consistency suggests that nature is built on balance rather than preference. Matter is not favored because it is more correct, but simply because conditions led to its dominance. Feynman's genius was in making this abstract symmetry understandable. Through his work in quantum electrodynamics, he showed that interactions between matter and antimatter could be described with astonishing clarity. When a particle emits or absorbs energy, antimatter follows the same steps, the same probabilities, and the same rules. There is no hidden exception carved out for antimatter. It plays the same game, on the same board, with the same rules. This realization quietly breaks the brain because it means antimatter is not a foreign intruder in the universe. It is a natural outcome of the same logic that produces atoms, light, and forces. If electrons exist, positrons must exist. If protons exist, antiprotons must exist. Denying antimatter would require rewriting the laws of physics themselves. Nature does not allow that inconsistency. One of the most striking consequences of this symmetry is seen in how matter and antimatter respond to forces. A positron placed in an electric field accelerates just as an electron would, except in the opposite direction because of its opposite charge. Place antimatter in a magnetic field, and it curves in the mirror image of matter's path. These are not guesses or theoretical hopes. They are observed facts, measured repeatedly in laboratories around the world. Even gravity, long suspected as a possible exception, appears to treat antimatter the same way it treats matter. Experiments continue to refine this measurement, but all evidence so far suggests that antimatter falls downward, just like matter. If confirmed fully, this would mean that even gravity respects the deep symmetry Feynman helped illuminate. The universe does not discriminate between matter and antimatter in its most basic attraction. What makes this symmetry profound is that it forces us to confront the idea that the universe could have been very different. In the earliest moments after the Big Bang, matter and antimatter should have been produced in nearly equal amounts. The laws of physics did not favor one over the other. Yet today, the observable universe is overwhelmingly made of matter. This imbalance is not written into the rules themselves. It is an outcome of subtle processes that slightly favored matter during the universe's infancy. Feynman's work sharpened this mystery rather than solving it, by showing how perfectly antimatter fits into the same framework as matter. He made the absence of antimatter even more puzzling. If antimatter is governed by the same laws, why is it so rare? Why do galaxies, stars, and planets appear to be made almost entirely of matter? These questions remain open, and they stand among the deepest in modern physics. Another layer of symmetry emerges when considering particles beyond electrons and protons. Every quark has an antiquark, every lepton has an antilepton. Even short-lived particles created in high-energy collisions appear alongside their antiparticle counterparts. The universe, at its core, seems to prefer pairs. Creation is balanced, mirrored, and symmetrical, at least in principle. This pairing is not decorative. It is essential for the consistency of quantum field theory. Feynman diagrams made these relationships visible. In these diagrams, particles and antiparticles are drawn interacting through the exchange of energy. The same diagram can often be read in multiple ways, depending on how time is interpreted. A particle moving forward can be reinterpreted as an antiparticle moving backward. This visual language reinforced the idea that matter and antimatter are two faces of the same underlying reality. What is especially striking is that these diagrams produce predictions that match experiments with extraordinary precision. Measurements of how electrons and positrons interact agree with theoretical predictions to many decimal places. This level of accuracy is almost unheard of in science. It means that the symmetrical treatment of matter and antimatter is not an approximation, but a near perfect description of how the universe works. The sameness of laws also means that antimatter can form structures similar to matter, at least in principle. Antimatter atoms can exist, with positrons orbiting antiprotons in the same way electrons orbit protons. Antihydrogen has been created and studied in laboratories, and its behavior closely mirrors that of ordinary hydrogen. Spectral lines, energy levels, and transitions appear nearly identical. This reinforces the idea that antimatter is not chaotic or alien, but orderly and predictable. This realization reshapes how we think about reality itself. If antimatter obeys the same laws, then the universe does not fundamentally distinguish between positive and negative, forward and backward, particle and antiparticle. These distinctions matter to us because of how we experience the world, but at the deepest level, nature is more neutral. It allows multiple possibilities, governed by symmetry rather than preference. Feynman's contribution was not merely technical, it was philosophical. He helped physicists accept that symmetry is not just an aesthetic feature of equations, but a guiding principle of existence. The universe is not built from isolated rules patched together, but from a coherent framework where consistency demands balance. Antimatter is a manifestation of that balance. This understanding also strips antimatter of much of its myth. It is not a substance that violates nature or threatens it by default. It is simply matter with signs reversed. The dramatic energy released during annihilation is not evidence of instability, but of completeness. When matter and antimatter meet, they convert fully into energy because the equations allow no leftover imbalance. Nothing is wasted, nothing is mysterious once the symmetry is understood. The idea that the same laws govern both also has practical consequences. Technologies that rely on antimatter work precisely because its behavior is predictable. Medical imaging techniques depend on the exact way positrons annihilate with electrons. Particle accelerators depend on the mirrored responses of particles and antiparticles to fields. None of this would be possible if antimatter followed different or unreliable rules. Perhaps the most unsettling implication is that a universe made entirely of antimatter could exist and behave almost exactly like ours. Stars would shine, atoms would form, chemistry would proceed. From a distance, it might be indistinguishable from a matter-based universe. This thought challenges the idea that our existence is uniquely tied to matter itself. What matters is not the sign of charge, but the structure of the laws. In revealing this, Feynman helped dissolve the boundary between the familiar and the strange. Antimatter feels strange because it contradicts everyday experience, but physics is not obligated to match experience. It is obligated only to be consistent. Antimatter satisfies that requirement perfectly. The brain-breaking aspect of this keynote is not that antimatter exists, but that it fits so well. It fits so neatly that denying it would tear the fabric of physics apart. The universe appears to be written in a language that naturally includes opposites, mirrors, and reversals, all coexisting within the same logical structure. Feynman's legacy in this area is a reminder that the deepest truths of nature are often quiet rather than dramatic. There was no explosion announcing that antimatter obeys the same laws as matter. There was only careful reasoning, precise calculation, and repeated experimental confirmation. Yet the implication is enormous. Reality is far more symmetrical and far less biased than human intuition suggests. As physics moves forward, this symmetry continues to guide research. new particles are searched for alongside their antiparticles. New theories are tested against how well they preserve these balances. Antimatter remains a benchmark for whether an idea truly respects the structure of nature. In the end, understanding that antimatter obeys the same laws as matter does more than clarify a scientific concept. It reshapes our sense of what is normal. It tells us that the universe does not privilege what we see every day. It allows opposites to exist naturally, governed by the same rules, woven into the same reality. And once this is understood, the universe feels both more logical and more mysterious than ever before. Few ideas in physics are as unsettling, counterintuitive, and quietly revolutionary as the one Richard Feynman helped popularize: the notion that antimatter can be understood as ordinary matter, moving backward in time. This idea does not come from science fiction, philosophy, or speculation about time machines. It emerges directly from the mathematics of quantum theory, and once taken seriously, it changes how we think about causality, time, and the flow of reality itself. To appreciate why this idea is so powerful, it helps to remember that physics does not begin with intuition. It begins with equations. When physicists describe particles mathematically, they are not describing tiny billiard balls, but abstract objects whose behavior is governed by probability, amplitudes, symmetries, and conservation laws. In this mathematical world, time is not experienced emotionally or psychologically. It is a variable, much like position or energy. And unlike human experience, the equations of fundamental physics do not strongly prefer one direction of time over the other. This becomes especially clear when studying relativistic quantum mechanics. When equations describe particles traveling close to the speed of light, they naturally allow solutions that look strange from a human point of view. Some solutions appear to move forward in time with positive energy. Others appear to move backward in time with negative energy. Early physicists found this deeply troubling. Moving backward in time sounded impossible, and negative energy seemed nonsensical. Yet the equations stubbornly refused to eliminate these solutions. Richard Feynman's genius was not in rejecting these strange outcomes, but in reinterpreting them. Instead of seeing a particle moving backward in time as unphysical, he realized it could be reinterpreted as a different particle moving forward in time. Specifically, a particle with reversed charge, reversed quantum numbers, and reversed direction in time could be seen as an antiparticle. This reinterpretation did not change the mathematics at all. It changed only how we understand what the mathematics is telling us. In this view, a positron is not an exotic object created by adding new rules to physics. It is simply an electron viewed from a different direction in time. When an electron appears to move backward through time in the equations, we observe it as a positron moving forward through time. The particle does not literally rewind history in the everyday sense, but its mathematical description carries the signature of reversed time flow. This idea is shocking because it suggests that time, at the deepest level of reality, is not as rigid as it feels to us. Human experience is built around a clear arrow of time. We remember the past, not the future. Causes come before effects. Broken objects do not spontaneously reassemble, but none of these experiences are fundamental laws of physics. They are emergent patterns that arise from statistical behavior, entropy, and large numbers of particles. At the level of individual particles, the laws themselves are almost indifferent to time's direction. Feynman's interpretation reveals that antiparticles are not violations of time's arrow, but reflections of its symmetry. The equations allow interactions to be read forward or backward in time without contradiction. What we interpret as annihilation, for example, can be seen as a particle and antiparticle meeting and converting into energy. But mathematically, the same process can be read as energy producing a particle-antiparticle pair. The direction of time determines how we narrate the event, not how the equations function. This flexibility becomes clear in Feynman diagrams, which revolutionized how physicists visualize particle interactions. In these diagrams, time is usually drawn as a vertical axis. Particles move upward through time. Antiparticles are often drawn as lines moving downward, as if traveling backward in time. Yet the diagram remains valid and predictive regardless of how it is interpreted. The physics does not break. The calculations remain consistent. This visual language made it easier for physicists to accept that time reversal was not a metaphor, but a legitimate way to understand antimatter. What makes this interpretation so powerful is that it simplifies calculations while preserving accuracy. Treating antiparticles as particles moving backward in time removes unnecessary complications from equations. It reveals hidden symmetries and ensures that conservation laws are respected automatically. When something simplifies mathematics and improves predictive power without contradicting experiments, physicists pay attention. This was not philosophical poetry, it was practical science. The idea also reshapes our understanding of causality. In everyday life, cause precedes effect. In quantum physics, interactions are not always so straightforward. Virtual particles appear and disappear. Processes occur that cannot be neatly ordered in time. By allowing particles to move backward in time mathematically, the theory accommodates these strange processes without violating observable cause and effect relationships. Reality remains stable at the human scale, even if it is flexible at the quantum scale. It is important to understand what this idea does not mean. It does not mean that antimatter allows messages to be sent into the past. It does not mean that time travel, as imagined in movies, becomes possible. The backward in time interpretation is a mathematical tool, not a practical mechanism. It describes how equations behave, not how macroscopic objects experience time. Yet dismissing it as just math misses the point. Mathematics is the language of physics. When that language speaks, it is describing reality, even if the description feels alien. One of the most unsettling consequences of this idea is how natural antimatter becomes. Instead of being a mysterious counterpart added to the universe, antimatter emerges as an inevitable feature of time, symmetric laws. If the equations allow motion backward in time, then antimatter must exist. Its presence is not optional. It is the price of consistency. This interpretation also deepens the mystery of the universe's beginning. If matter and antimatter are connected through time symmetry, then the early universe must have been governed by processes that treated both almost equally. The fact that matter dominates today suggests that some tiny asymmetry broke this balance. Understanding that asymmetry requires understanding how time, symmetry is subtly violated in certain interactions. Antimatter, therefore, is not just about particles. It is about why time seems to flow the way it does. There is also a philosophical weight to this idea that cannot be ignored. Human intuition insists that time is fundamental, directional, and absolute. Feynman's interpretation suggests that time may be more like a coordinate than a command. It flows forward for us because of how complex systems behave, not because the universe demands it at every level. Antimatter exposes this uncomfortable truth by living at the edge of time's symmetry. Experiments continue to confirm the predictions that arise from this interpretation. Particle collisions behave exactly as expected when antiparticles are treated as time, reversed particles. Lifetimes, decay rates, and interaction probabilities all match theoretical predictions with astonishing precision. These confirmations do not prove that antimatter is really moving backward in time in a literal sense, but they prove that treating it that way captures something deeply real about how nature works. Perhaps the most brain-breaking aspect of this keynote is not the image of particles reversing time, but the humility it demands. It reminds us that our everyday experience of time is not a reliable guide to the universe's foundations. The cosmos is not built to make sense to human instincts. It is built to obey mathematical consistency. Feynman was famous for insisting that nature cannot be fooled. You can dress up ideas in comforting language, but experiments will expose what is wrong. The backward and time interpretation survived because it worked. It made correct predictions. It aligned theory with reality. That alone gives it weight, regardless of how strange it feels. In the end, this idea forces a quiet but profound shift in perspective. Antimatter is not just the opposite of matter. It is a window into the deeper symmetry of time itself. It shows that the universe is comfortable allowing processes that challenge human storytelling, as long as they preserve mathematical truth. Once this is understood, antimatter stops being merely exotic and starts becoming philosophical dynamite. It tells us that past and future are not as sharply separated as they feel. It tells us that reality, at its core, is not organized around human perception, but around deeper principles of balance and symmetry. Feynman did not claim to fully understand time. No physicist does. But by showing that antimatter can be interpreted as matter moving backward in time, he revealed something essential. The universe is far stranger than linear narratives allow, and time itself may be one of the most flexible ingredients in the cosmic recipe. That realization lingers long after the equations are put away. It leaves behind a quiet unease and a deep respect for the power of physics to overturn assumptions we didn't even realize we were making. Antimatter, through Feynman's insight, becomes more than a particle. It becomes a challenge to how we understand reality itself. When matter and antimatter meet, the universe performs one of its most dramatic and revealing acts. In that instant of contact, mass vanishes and energy is released with perfect efficiency. There is no ash, no residue, no leftover substance. Everything that defined those particles as matter is transformed into pure energy. This process, known as annihilation, is not just a spectacular reaction. It is a window into the deepest rules governing reality. Richard Feynman's work helped make sense of this phenomenon, showing that it is not a violent exception to nature's laws, but one of their most elegant expressions. At the heart of this process lies Einstein's famous equation, E equals mc2. This equation states that mass and energy are two forms of the same thing, connected by the square of the speed of light. In everyday experiences, this conversion is almost invisible. Chemical reactions convert only tiny fractions of mass into energy. Even nuclear reactions, as powerful as they are, leave most of the mass intact. Matter-antimatter annihilation is different. It converts nearly 100% of mass into energy. Nothing else in the known universe does this so completely. This is why matter-antimatter interactions are often described as the most powerful energy releases possible. A single gram of antimatter annihilating with a gram of matter would release energy comparable to a large nuclear explosion. Yet focusing only on the power misses the deeper meaning. The annihilation process is not about destruction, it is about balance. Matter and antimatter carry opposite charges and quantum numbers. When they meet, these opposites cancel perfectly, leaving behind energy that obeys conservation laws with astonishing precision. Feynman's insights into particle interactions clarified why this process is so clean and unavoidable. In quantum electrodynamics, particles interact through exchanges of energy and momentum that must obey strict mathematical rules. When a particle meets its antiparticle, there is no allowed state in which they can coexist peacefully. The equations demand that they convert into something else, usually photons. This is not a choice or a tendency, it is a requirement of consistency. What makes this interaction so striking is its symmetry. The annihilation of matter and antimatter is the mirror image of pair production, where energy transforms into a particle-antiparticle pair. In high-energy environments, such as near stars, black holes, or particle accelerators, energy can condense into matter and antimatter simultaneously. Later, when these particles encounter each other again, they reverse the process. Creation and destruction are two sides of the same coin, governed by the same rules. This symmetry reveals a profound truth. The universe does not distinguish between making matter and destroying it. Both processes are natural, reversible, and mathematically equivalent. What we call annihilation is simply energy changing its form. Sino pork, tu cambias, tu forma de estar en ale. Everything is accounted for. The immense energy released in these interactions is not chaotic. It emerges in precise, predictable ways. When an electron meets a positron, they typically produce two gamma-ray photons moving in opposite directions. The energies and directions of these photons are tightly constrained by conservation laws. Experiments confirm these predictions with extraordinary accuracy. The universe does not waste energy or violate its own bookkeeping. This precision is one reason antimatter is so valuable in science. By studying annihilation products, physicists can test fundamental theories with extreme sensitivity. Small deviations from predicted energies or angles could signal new physics. So far, the results have confirmed existing theories again and again, reinforcing confidence in our understanding while also highlighting how little room there is for error. Beyond laboratories, matter-antimatter annihilation plays a role in some of the most extreme environments in the cosmos. In regions near neutron stars and black holes, enormous energies can produce particle-antiparticle pairs. When these pairs annihilate, they contribute to intense radiation, including gamma-ray bursts. These bursts are among the most energetic events observed in the universe, briefly outshining entire galaxies. Such cosmic events remind us that antimatter is not rare because it is weak or unimportant. It is rare because conditions must be extreme to produce it in large quantities. When those conditions are met, antimatter behaves exactly as the laws of physics predict, releasing energy with unmatched efficiency. Feynman's work helps explain why annihilation is so efficient by emphasizing the role of symmetry and conservation. Matter and antimatter are perfectly matched opposites. When they combine, there is no leftover imbalance. The conversion to energy is complete because the equations allow no alternative outcome. This is nature at its most decisive. The idea that the universe allows such efficient energy release raises obvious questions about why it does not happen all the time. Why doesn't ordinary matter spontaneously annihilate? The answer lies in separation. Matter dominates the observable universe, and antimatter is scarce. Without antimatter present, annihilation cannot occur. Stability is not due to weakness in the process, but due to the absence of suitable partners. This scarcity itself is a deep mystery. According to current understanding, the early universe should have produced matter and antimatter in nearly equal amounts. If that balance had been perfect, everything would have annihilated, leaving behind only radiation. The fact that matter survived suggests that tiny asymmetries tipped the balance. Understanding these asymmetries is one of the great challenges of modern physics, and matter-antimatter annihilation sits at the center of this question. The practical power of annihilation has captured human imagination for decades. Science fiction often portrays antimatter as a fuel source or weapon. While the energy potential is real, the practical challenges are enormous. Producing antimatter requires vast amounts of energy. Storing it safely requires preventing contact with ordinary matter, which is extraordinarily difficult. From a practical standpoint, antimatter is not an efficient energy source with current technology. Yet even without futuristic applications, annihilation has already found practical use. In medical imaging, positron emission tomography relies directly on matter-antimatter annihilation. Positrons emitted by radioactive tracers annihilate with electrons in the body, producing gamma rays that can be detected to form detailed images. This technology demonstrates that annihilation is not just a cosmic spectacle, but a tool for understanding and improving human health. What makes annihilation particularly fascinating is how it reinforces the idea that mass is not fundamental. Mass is a form of stored energy held together by fields and interactions. When matter meets antimatter, that stored energy is released. This supports a view of the universe where energy is the primary currency, and matter is just one way it can be organized. Feynman often emphasized that physics is not about naming things, but about understanding how they behave. Matter-antimatter annihilation exemplifies this philosophy. Calling it destruction can be misleading. Nothing is destroyed. The system simply changes state. Energy that was locked into mass becomes free to propagate as radiation. This perspective changes how we think about power. The most powerful energy releases are not explosions driven by instability, but transformations driven by symmetry. The universe does not need violence to produce power. It needs only balance and the freedom to change form. There is also a philosophical weight to this idea. Annihilation shows that opposites can cancel perfectly, leaving behind something entirely different. This is not just a physical process, but a metaphor for how the universe resolves contradictions. Instead of choosing one side, it allows both to exist until they meet, and then it transforms them into something new. Feynman's contribution was to demystify this process without diminishing its wonder. By showing how annihilation emerges naturally from quantum electrodynamics, he removed the sense that it was an exotic or dangerous exception. It became a predictable, calculable outcome of well-understood laws. The brain-breaking aspect of this keynote lies in the realization that the universe contains mechanisms capable of converting reality itself into pure energy, and that these mechanisms are not rare accidents but fundamental features. Matter and antimatter are not enemies in a cosmic battle. They are complementary expressions of the same underlying structure. Understanding this reshapes how we see the universe's power. The stars shine not because matter is fragile, but because energy transformations are possible. The cosmos evolves not by destroying what exists, but by continuously rearranging energy into new forms. As experiments grow more precise and theories more refined, matter-antimatter annihilation remains a touchstone for understanding energy, symmetry, and conservation. It stands as a reminder that the most extreme phenomena are often the clearest expressions of fundamental principles. In the end, what Feynman helped reveal is that the universe's greatest power lies not in its capacity for destruction, but in its capacity for transformation. Matter-antimatter interactions do not break the laws of physics. They display them in their purest, most uncompromising form. And once this is understood, the immense energy released in these encounters feels less like a threat and more like a signature of a universe that is deeply, elegantly, and relentlessly consistent. Richard Feynman's insights into antimatter did far more than clarify a strange class of particles. They helped unlock the entire framework of modern particle physics, reshaped how forces are understood at the quantum level, and quietly influenced how we think about the origin and fate of the universe itself. His contribution was not a single discovery carved in stone, but a way of thinking that made the invisible structure of reality intelligible, calculable, and testable. Through this lens, antimatter became a key that opened doors far beyond its own mystery. Before Feynman's work reached maturity, quantum physics was powerful but unwieldy. Equations existed, but they were difficult to interpret and even harder to use for real calculations. Predictions could be made, but only with extreme effort, and often with confusing infinities that seemed to threaten the validity of the theory itself. Physicists knew that electrons and light interacted, but describing those interactions precisely felt like navigating a maze without a map. Antimatter, with all its strange implications, only added to the confusion. Feynman changed this landscape by reimagining how particle interactions could be described. Instead of wrestling endlessly with abstract equations, he introduced a visual and conceptual framework that turned complex mathematics into understandable processes. His diagrams did not replace the equations, they revealed their meaning. In these diagrams, particles, antiparticles, and forces interacted in ways that could be followed step by step. Antimatter was no longer a mysterious add-on. It became an essential actor in every fundamental interaction. This approach transformed quantum electrodynamics, the theory describing how light and charged particles interact. QED became the most precisely tested theory in the history of science. Predictions made using Feynman's methods matched experiments to extraordinary accuracy, sometimes agreeing to more than 10 decimal places. This level of precision is not a coincidence. It is a sign that the underlying ideas capture something profoundly true about how the universe works. Antimatter played a central role in this success. Virtual particle-antiparticle pairs appear constantly in quantum processes, even in empty space. They influence forces, shift energy levels, and subtly modify interactions. Without antimatter, these calculations would fail. Its presence is not optional or decorative. It is required for the theory to function correctly. The vacuum itself, once thought to be empty, turned out to be a restless sea of fleeting particles and antiparticles, shaping reality from beneath the surface. This realization marked a turning point in physics. Empty space was no longer empty. It became an active participant in the universe's behavior. Forces emerged not as simple pushes and pulls, but as consequences of quantum fields filled with constant activity. Antimatter was woven into this picture at every level. It helped reveal that the universe is not made of isolated objects, but of interacting fields whose excitations we perceive as particles. Feynman's influence extended naturally into the development of the standard model of particle physics. This model unifies our understanding of fundamental particles and forces, excluding gravity. Every particle in the model has an antiparticle. Their interactions are described using the same diagrammatic and conceptual tools Feynman helped develop. Without his insights, the standard model would be far less coherent and far less predictive. The success of this framework reshaped how physicists approached new discoveries. When new particles were predicted or found, their antiparticles were expected as well. Experiments were designed to search for both simultaneously. The idea that nature prefers symmetry became a guiding principle. Even when symmetries were found to be broken, the breaking itself became a subject of deep investigation rather than an inconvenience. This focus on symmetry and its violations led directly into cosmology. Understanding antimatter is inseparable from understanding the early universe. In the moments following the Big Bang, temperatures and energies were so extreme that particles and antiparticles were created and destroyed continuously. The universe was a boiling quantum environment where matter and antimatter existed in near balance. Feynman's tools and interpretations allowed physicists to model these conditions with increasing realism. One of the most profound questions in cosmology is why this balance did not persist. Why did matter survive while antimatter largely disappeared? The answer appears to lie in subtle violations of symmetry, where the laws of physics treat matter and antimatter almost, but not exactly, the same. These tiny differences, amplified over cosmic time, may have determined the structure of the universe itself. Without the conceptual clarity Feynman brought to particle interactions, these questions would be nearly impossible to frame, let alone answer. His work made it possible to connect laboratory experiments with cosmic history. Measurements made in particle accelerators became clues to events that occurred billions of years ago. Antimatter became a bridge between the very small and the very large. Feynman also influenced how physicists think about probability and uncertainty. In quantum theory, outcomes are not determined with certainty, but with likelihoods. Antimatter contributes to these probabilities through virtual processes that cannot be directly observed, but have measurable effects. This reinforced a view of reality that is fundamentally statistical, where certainty emerges only at large scales. This shift in thinking had philosophical consequences as well. It challenged the idea that reality must be deterministic and intuitive. Instead, it suggested that nature operates according to rules that are precise, but not always predictable in detail. Antimatter, appearing and disappearing in quantum fluctuations, embodied this strange balance between order and uncertainty. The methods Feynman developed also influenced generations of physicists. His emphasis on physical intuition, simplicity, and honesty reshaped scientific culture. He insisted that theories must correspond to observable reality, not just mathematical elegance. Antimatter survived this scrutiny precisely because it worked. It produced correct results, explained experiments, and led to new predictions. In this sense, antimatter became a proving ground for modern physics. If a theory could handle antimatter correctly, it was likely on the right track. If it could not, something fundamental was missing. This standard pushed physics toward greater coherence and deeper understanding. The influence extended beyond academia. Technologies rooted in particle physics, from medical imaging to materials science, rely on principles that include antimatter at their core. These applications are indirect, but they are real. They demonstrate that understanding the universe at its most fundamental level can produce tangible benefits, even when the original motivation was pure curiosity. Feynman's legacy is also visible in how physicists communicate ideas. His diagrams and explanations made abstract concepts accessible without oversimplifying them. Antimatter could be discussed not as a mystical opposite, but as a natural consequence of symmetry and conservation. This clarity helped demystify science without stripping it of wonder. The brain-breaking aspect of this keynote lies in recognizing how much of modern physics depends on ideas that once seemed impossible. Antimatter was not discovered because it was useful, but because it was unavoidable. Feynman's work showed that embracing such ideas, rather than resisting them, leads to progress. Through antimatter, physics learned to trust its own logic even when it defied intuition. This trust unlocked a deeper understanding of forces, particles, and the universe itself. It revealed that reality is not built from common sense, but from consistency. As cosmology advances and new theories attempt to unify gravity with quantum mechanics, the influence of Feynman's approach remains strong. Any successful theory must account for antimatter, symmetry, and quantum interactions with the same precision achieved in QED. The bar he helped set is extraordinarily high. In the end, Feynman did not just explain antimatter. He showed how to think about it. He demonstrated that the strangest features of the universe are often the most informative. By following them carefully, without fear of their implications, physics can uncover structures that connect the smallest particles to the largest cosmic questions. Antimatter, through Feynman's insights, became more than a mirror of matter. It became a foundation stone of modern science. It helped turn physics into a unified narrative, where equations describe not only what exists, but why it exists at all. And once this is understood, it becomes clear that antimatter did not just challenge our understanding of the universe, it helped build it.